Students, welcome to lecture number 14. So, we are slowly closing in about the ML models. So, last lecture I discussed about support vector machine, what is popularly known as SVM. SVM has different avatars. The classical one is what I am teaching, how this can be used as a decision boundary problem. So, this is the lecture number 14 in which we are going to speak mostly about SVM. Second part of lecture I will start discussing about the artificial neural network. We will start discussing about it and we will elaborately discuss ANN in the next lecture, that is lecture number 15. So, as you know, we have started with the linear models, then we discussed about DT, earlier we discussed about probabilistic approach like Bayesian, and now we are discussing SVM. We will slowly move to NN or ANN, and rest of the things are clustering, model selection, visualization and transformation. This is a very big portion of this course. So, what are the things we learn? Well, support vector machine is one of the best decision bound problem. Okay. This is what we call decision boundary problem. So, what is it? Let me just briefly tell you. Suppose I have data plus and minus, maybe this is in a hospital, some people are diseased, some people are not diseased, and so we can denote one plus category, that means non diseased as closed circles and diseased one as a open circle. You can also think about in a cancer treatment, some tumor which is benign can be marked as a closed circles and malignant can be marked as a open circles. So, now if I have to decide on a machine learning algorithm to separate them out, I can always think of drawing a line, right, very simple line, that is a boundary between these two. But as I told you, if you think of this problem very carefully, you can draw many lines. This is another line, you can draw another line and you can draw many such lines between these two sets of data points. So, what is the unique line then? Is there a unique line? Why it is important? Because of the fact that if I have to develop a model which can predict any new say new instances or new instances such that either it will fall on the plus or minus category, how do I make that boundary between this plus and minus? That is what I told you that this is a decision boundary problem. How we can solve this problem? Very simple. We will go to the board soon and discuss about it. We can actually, instead of drawing a line, we can basically draw a road. Okay. And as you can see, this is a red color road and there is a center line which is drawn as a black line. So, as usual, the road has two sides and center line is passing through the center of the road. So, one side can be positive, other side can be negative. So, here top one is positive, that plus 1, bottom side is negative. And the road is drawn in such a way, it is touching some of the positive points and some of the negative points. You can see here, correct. So, basically these points are touching or just sitting at the boundary of this road, or we call it gutters of the road. Okay. So, idea should be actually, if you want to make the decision perfect or predictions of the decision perfect, you should make this width of the road as big as possible. Then you have no chance of making any mistake or misclassification, right. That is the main idea of support vector machine, which was discovered by a Russian scientist. I talked about it on last class. Okay. So, as you know, this is what we can talk about it. You can see this road is much wider, right. So, and these data points which are sitting at the boundaries, they are basically pushing the boundaries quite a bit, right. So, hence I should draw the road in such way, these data points to sit on the boundaries of the road and there will be a center line, and that is what is called a maximum margin linear classifier. Okay. The width of this road is maximum. Okay. Let me use a different color so that you can see it nicely. So, width of the road is this, right. So, if that is as big as possible, then I call it maximum boundary linear classifier, right. Well, there are nonlinear classifier also. So, we can talk some other time, but let us focus on these. Okay. So, these points which are sitting on the boundaries are called support vectors. Why? These are the points that the margin pushes up against, okay, because these data points are at the points which are demarcating the boundaries or the gutters of the road, right. So, these points are called support vectors. Since it is a machine learning algorithm, we call a support vector machine. Okay, we could have called it support vector machine learning algorithm, but anyway, we always cut short in real life and we call it support vector machine. This is a classical linear classifier. You have seen decision tree also as a classifier, right. We can subclassify things. Here it can classify things in a 2D or 3D plots also. So, why the road has to be as big as possible? Very simple. Intuitively it is feels safest, because then you can put as many data points as possible. Most important thing, if we make a small error, let us say in location of this boundary, then what happens? This gives you least chance of causing a misclassification, sorry. That means it gives you a very small error. That is the main aspect of this. Today we will discuss in the board how we can develop this algorithm, so that road can be maximized, width can be maximized, right. So, let us go back to the board. I will draw some construction which I had drawn last class, sorry, first. So, this is suppose my plot is, okay. So, I draw simply 2 negative points and 2 positive points, okay, just like I drawn it in last lecture, and then I draw my board, sorry, to draw my road actually. So, first is I draw this boundary, and then I also draw this boundary. Am I clear? So, then I draw the center line. You could have traveled on Indian roads, you could have seen there is center line and traffic moves on the both sides. So, this is what is my road is. Okay. So, I said this side of the road, that means the one which is sitting on the right side of yours, right side of the center line, they will all contain positive points. So, therefore, I can call this as a positive line, am I right? And this I can call as a mean line, okay, mean, and this one is called, I can call as a negative line. So, anything sitting or falling on this area or beyond this area can be called as a positive points. Anything sitting on this line or on this side of the road, this side means left side of this middle line, anywhere, even on the gutters also, I call it a negative points. So, that is how we can classify things nicely. But in order to make this classification perfect, rather in order to make this classifier the best one, I must have this width as big as possible, right. This width should be as big as possible. Many people call this as a margin also, as you have seen in my lecture slide, this is called a margin. So, I can make, if this I can make this width as big as possible, or rather maximize the width or maximize the margin, my job is done. Then I will be making the best, one of the best classifiers. So, how do I do it? Well, I told you first thing what I did in the last lecture. Let me go back. So, I draw first a vector from here W, which is perpendicular to this center line. Let us say this is a vector which I had drawn, it is basically perpendicular to center line in such a way. So, now I draw also a vector from here. Let us say this is u, unknown, negative. Okay. This is a vector from u. So, now I can explain things very nicely, please listen carefully. So, I have drawn two vectors, one both from the origin, one basically vector is like w, which is perpendicular to the center line. Am I clear? I have drawn another vector u, which is unknown, okay, which is basically joining this data point, negative data point and the origin. These two are vectors. So, now I can think the problem like this. If I project this u vector onto W, if I project this u vector to W, so this will be longer, right, this is projecting. So, that vector, the projected vector, if it crosses beyond this main line, the data point must be positive. If this projected vector does not cross the main line, or rather falls below the main line, then it is called a negative point. I can easily classify that. Okay. So, okay, let us do that mathematically, very simple. So, I have a vector called W, correct, which is drawn such a way that is perpendicular to main line. I have a vector called U. Okay. I take a dot product of these vectors, right, projection means dot product, right. So, you know that fundamentally speaking, I can write down this as a W U cos theta, okay, and if I can mark even this angle as a theta, right, I can do that, right. So, that is okay, forget about all these things, that is what is called vector algebra, let us not do that. So, I can write down that. So, the thing I am discussing, I project this u vector into W and then look at this vector length of the vector, whether it crosses the midline or not. So, if it crosses the midline, okay, if this vector is greater than some critical value means what? Dot product is always a you know, it is not a, it is a scalar quantity, any dot product is a scalar quantity. If this dot product is more than a critical value C, then let us say it become a positive, correct. If it less than C, then it is negative point. So, fundamentally speaking, these two are my decision rules, right. Fundamentally speaking, am I clear? So, when this vector, the u vector projected onto W has certain critical value, so that the vector projected crosses the midline, it is called a positive point. When this projected vector to W does not cross the midline or less than critical value C, it is a negative point, very simple. We can write down this equation even much better way. Okay, where B is very simply minus C, right. Am I clear? We can do that. So, we have taken this C from this side minus C and done that. I have done no new mathematics. So, therefore, this equation tells me that this is how decision to be done, decision to be made, right. In order to do that, in generality, what we can do? In general, we can write down that then this is positive, this is negative. Okay. So, this is general decision rule. Or decision rules actually, correct, these two. So, I can always, it is better to put like this, because lines are placed plus and minus. So, what we need to do is here we need to find out the value of W, value of B, because unknown vector is known here. So, these two are the values I must find out, then my classification algorithm is done. So, we can find out the values of W B obviously from data analysis, but mathematically also we can find out, we will see that. Okay. So, first if you want to do this, what should you do? Okay, let us first let us keep this one, and maybe I should erase some of these things, so that you can understand and keep this construction. Well, let us first take two important aspects. One, obviously I can write down this in a matter way, these two equations. If I say this is u is u positive, that means u positive means positive values, correct. Am I clear? We can always write down that, or we can also write u negative Am I clear? Just to classify, if this is positive, so for all values, all positive instances, this is for all negative instances. Okay. This actually coming from this only. So, let me just write down this. Let us say this is 1, this is 2 and this is 3 set of equations. Okay. These are coming from this only. Okay. So, does it mean that it basically categorically classifies things, negative, positive, right, categorically, you do not make any mistakes. Here you have more than less than 0. So, that is also positive, negative, something more than 0 is positive, something less than 0 is negative, but here we are categorically writing -1 and +1. So, that you do not have problem of any misclassification, that is the difference. So, now let me go back here, whatever space, let us say I have a vector x plus, okay. Sorry, I have a vector y, I define vector y, yi, okay, and I say yi is positive for all positive instances. I have written like here also. This is a mathematical process, do not worry about it, and yi is negative for all negative instances. Am I clear? So, now if I multiply this yi with these two equations, what shall I get? Okay. So, let us do that. If I multiply, remember yi is a separate variable I declared. I define this yi, okay. So, this is mostly y and this is x, right, okay. Here it is u. Am I clear? So, this is y, that is what you do, y or x, y or u does not matter. So, this is u. So, now I define yi such way that is positive for all positive instances, negative for negative, that is very simple. So, if I do that, then it become, because we are multiplying with a positive number multiplied with this must be positive, correct, because this is u is also positive. Now, if I multiply with yi when it is negative, then also it will be positive. Why? Because if I multiply negative number, the sign indicating for the inequality sign will be reversed, as you know in mathematics. Okay. So, what does it mean? Whatever the value of yi, whether it is positive or negative, correct, the identity become or the inequality becomes similar. So, that means in general I can write down yi dot w bar w vector u plus b is equal to 1 in general. Okay, both of them are equal to 1. So, I can always write down equal to 1, right. Some people can say why you want to write equal to 1, you can write down even this also. That is much smarter mathematical equation. Okay. So, this is what is my final equation, right. So, this is for all use what sitting on the all use on the gutter. Why? Which are points are sitting on the gutter. So, these points which are sitting at the gutter, this one, this one, this one, they are all support vectors, right. I discussed just now. These are all support vectors. Why? Because they are the ones by through which these boundary lines are passing through. If they are sitting wider, the boundary lines will sit wider. If they are sitting nearby, boundary lines will be nearby. So, this is what the boundary line pushes. This point boundary line will push, try to push as much as. So, when you draw this road, you have to draw in such way, whatever angle you possibly you can draw, it is a linear classifier, whatever angle you draw in such way these points actually sitting on the gutters or sitting on the ends of this road. Okay. That is the meaning of this. So, this equation value is for all the u's which are sitting on the gutter. So, then you do not need u plus or u minus, it is basically simply u. Okay. That is the first important mathematical equation we can derive, okay, other than the decision boundary rules or decision rules. Okay. I hope this much is clear to you. So, now how do I maximize, right? How do I maximize W? Okay. So, if you look at this problem, this is a problem which is related to what is known as a constraint maximization. Okay. Let me erase this. Constraint maximization. What is constraint maximization? I hope you know it. If you do not know it, let me explain to you. So, that means this problem, this problem is known as a constraint optimization. Optimization can be maximization, minimization. That means what? Let us say I have y is equal to x square. I want to maximize this under the condition that both x and y lie on a circle defined as, okay. This is what is called constraint optimization. If I simply say maximize this function or find out the maxima, so you will simply say, okay, I take first derivative dy dx, that is your 2x, put it 0, so x becomes 0. Okay. So, now I take the second derivative, which is 2, which is always positive. So, therefore, at x is equal to 0, y is y max, because first derivative 0, second derivative is more than 0. Sorry, y mean is not max, it is positive, right, minimum value. But that is not, that is open optimization, there is no constant. The moment you say you have these two x and y lie in a circle, that must satisfy this equation. So, you can then y, then x square becomes, so you have to write down max for maximization y is equal to x square plus lambda x square plus y square minus 1, okay, because this is x square plus y square minus 1 equal to 0. This lambda is known as a Lagrange multiplier, or what is called as a Lagrange multiplier. I thought I should discuss with you in case you do not know. Okay. So, this problem which you are handling here, it is a constant optimization problem. Why? Because you have data points sitting on the roads. So, therefore, these data points are the constraints. If data points lie close by, the road will be smaller, data points lie farther apart, roads will be wider. So, they are the one which are called constraint, which are creating constraint on this optimization principle. So, we have to use this equation. We will come back to the next lecture and we will show you what is the best possible way of understanding finding out this value of optimum value of W in terms of B. Okay, we will come back to it.